Welcome! In this video, I will share our solution to the 2020 Better Team campaign. I am Toyuan, or TY as well. I'm the first author and the narrator. Change point detection is designed to identify structural change in time series. With the support from the SCADA system, change point detection is promising for leak detection and will facilitate isolation tasks. At the very beginning of the proposed approach, we need to perform a benchmark simulation, assuming no leakage occurred, in the pressure-driven demand mode, using the WNTR package. As the pre-processing step, the demand data were simulated as the nodal pattern, and thus nodal demand residues are negligible. By comparing the sensor measurements with the mechanistic model predictions, we will derive the flow rate residues and the pressure residues, which quantifies the deviation from an intact or no leakage working condition to the current measurements. Adopting the residue series, we would perform the ensemble multivariate change point detection algorithms, or MCPD. In the first sub-step, we focus on the flow rate residues, in order to roughly detect occurrence times of leak events. In this part, the flow rate residues with 3 variables were averaged to 3 observations per day in order to denoise, keep diurnal or weekly cycles, and accelerate computation. After this sub-step, MCPD would have proposed rough time candidates of leak events. In the second sub-step, we employ both flow rate and pressure residues in order to accurately detect occurrence times of leak events. In this part, both the flow rate residues and the pressure residues were incorporated from 46 hours before to 2 hours after each rough time candidates. So after this sub-step, MCPD would have proposed accurate moment candidates of leak events. This two-sub-step arrangement is to accelerate computation and to filter short-term noises. With the detected moment candidates, now we perform the isolation step. In the first sub-step, we would draw the pressure contours using the bilinear bivariate spatial interpolation from 25 minutes before to 25 minutes after each accurate moment candidate. We draw the pressure contours using the real measured pressure time series from the pipes that are inside the convex hull that are spanned by the 34 pressure sensors. So after this sub-step, essentially we would have spatial temporal pressure series in short time periods around each detected accurate moment candidate. In the second sub-step, we will perform 2 sample one-sided students t-test with unknown variances for each pressure time series from each node. Firstly, we perform exponential smoothing. Then, the series were grouped as before or after the candidate. That is also forming the 2 samples to be statistically tested. Those with both pressure drop and minimal p-values were isolated. So notice that the sensors are sparse. We need to be conservative. Therefore, in this step, we are using real measured pressure data instead of residuals, and we do bilinear instead of bicubic. We do interpolation, but no extrapolation. We do one-sided test of unknown variance, but not two-sided tests with equal variance. And we set a low threshold of 0.01 for p-values. In terms of the MCPD components, we employed 6 algorithms to vote. The first one is the most recent change point detection. The second one is a known parametric version. The third one involves proving the objective, which is involving a dynamic programming. The fourth is a kernel one. The fifth is employing informative sparse projection, which involves convex optimization. The last one is a Bayesian one. It involves Bayesian model averaging, which is to alleviate model misspecification, address algorithmic uncertainty, and reduce overfitting. The votes from all algorithms were pooled to vote for the final candidate. And here are the detected results. We have 30 rough candidates and 50 accurate candidates. Actually, during the experiments, we observed that for the first substep, the votes were more scattered, but for the second substep, the votes were highly concentrated. And here are the isolation results. P-values are significant, and pressure shifts are all negative. As a summary, we fitted the mechanistic model with demand data simulated into the WNTR simulation. Then we proposed the two-step MCPD leak detection based on residues of different temporal resolutions. The detected candidates were further inspected and tested. The whole approach is hybrid, computationally efficient, and conservative. It could be run in parallel and could be transferred to other spatial temporal datasets if they have mechanistic models to be considered. For future research, we would investigate anisotropic spatial kriging methods to improve the isolation step performances. So that's it. Thanks for watching, and please feel free to comment or ask questions. I am TY and I'm happy to discuss with you. So see you next time. Thank you.